All right, now for the next lesson here on nuclear fission. Fission. Fission means to split things apart. Okay, so when something fizzes, like pour a pop can and Pepsi or something like that into a glass, it fizzes. It's kind of breaking apart. Think of it like that, I guess, is to help. It's not really the meaning of the word, but yeah, it means to break things apart. So Ernest Rutherford split the atom for the first time in 1919, and really wasn't people didn't realize the power, the potential that it had, and so it's led to major advances in medical. There's radiation therapy for treating cancers. There's radioactive isotopes that can put in to be able to like map out the cardiovascular system to find where a problem is in someone, or someone has a health problem of some sort. Um, huge implications in medical fields. Obviously, nuclear power generation, so the electricity generated by nuclear power, is majorly relied upon in Ontario. Our percentage is roughly 60% of our energy comes from nuclear. And obviously, unfortunately, nuclear weapons are devastatingly powerful, right? So with nuclear power generation, the good is, of course, that it has virtually no atmospheric pollution whatsoever. The only thing you're left up with is, of course, nuclear waste. Some things to know about nuclear waste, though, that there's a small amount of it. Like it takes, if you look at a giant mountain of coal, like a whole big pile of coal, how long that would provide energy for a town versus nuclear, the nuclear pellet that would provide the same amount as I think it's something like 24 Olympic swimming pools full of coal, is a little nuclear pellet the size of like the eraser of an millimeter pencil or something. It's unbelievable the potential, how much amount of energy stored in the nuclear material. So even though there's nuclear waste, of course, there's not a lot of it. But the other good is that we have the best. Canada has designed the best nuclear power process called the CANDU reactors, and yeah, they're super safe, and I'll show you why in a bit. The bad, of course, is the radioactive waste. But again, like I said, there's not actually really a lot of it because it doesn't take a lot of material to provide enough energy to power a town for a long period of time. The ugly, of course, is the danger, the radiation, the hazards, hazards that are associated with nuclear processes and problems. So if you have a nuclear meltdown, the reactor like melts down, they call it a meltdown, and so on, right? Radiation can obviously contaminate large areas and so on, and that would be a very big problem. But just know that one thing to know is that this is not a nuclear meltdown. This is not a nuclear power plant having an accident. That's a nuclear bomb, right? That's what that is, that picture. A nuclear meltdown is just the small amount of radioactive material they have in the reactor might get dispersed, but hopefully they don't tend to store large amounts near the reactor, of course, right? And if there was a meltdown, it's not a massive explosion. It's just it gets way too hot and things start to melt and whatever. CANDU reactor stands for Canadian Deuterium Uranium Reactors. And so they use deuterium, which is heavy water. So instead of being two hydrogens that have no neutrons, and one or both of the hydrogens have a neutron, so it literally makes the water heavier, and it makes it able to be what's called a moderator. And so a moderator is something that makes a nuclear chain reaction happen and be sustainable and produce more and more energy. So the reason CANDU reactors are so safe is because that water is used as a moderator. And so what you have is you have the nuclear fuel rods literally dipped into, I don't know if the picture shows, it doesn't really show super well there, but basically picture the nuclear rods, the nuclear material being on a machine that goes into a vat of heavy water. All right, and so when it's in the heavy water, whole bunch of nuclear reactions happen, and it releases a bunch of heat. Okay, and that heat boils. They've used the heat from that to boil water, and that makes steam, and that turns a turbine, and that turns a generator, and that produces electricity. So the really good thing about the CANDU reactor is that if this got out of control, this water would just boil off, and eventually the water level would go down below, right? Within not long, really, actually, the water level would go below the reactor rods, and the reaction naturally just stops. And so it's literally a 100% like fail-safe method. It's just if you run out of, if it gets out of control, it automatically stops on its own. Okay. And so just notice there, I did mention, the simplicity of a nuclear reactor is you have a nuclear reaction here that releases heat, and that just heats up water, which boils, heat boils water, makes steam. Steam drives through a turbine, turns a generator. Just like a gas-powered generator, it's a gasoline engine that's turning and making a generator turn. Instead, this is just high-pressure steam making a turbine turn. So I saw a meme or whatever you call this lately. It was hilarious. It's like how people think nuclear energy works. It's like magical, mysterious, right? You got like a nuclear bomb, and it makes energy somehow, and it's not at all. It's literally just boiling water, which I thought was funny when I saw that. So what we're focusing on is the physics of the actual heat production. And this is an engineering class about the engineering design of the nuclear reactor itself. It's more about the nuclear reaction that's releasing the heat. So Albert Einstein obviously discovered through his work that E equals mc squared. Basically, there's an energy mass equivalence, and that mass is equivalent to a lot of energy, right? And so you can release a lot of energy if you are able to convert any of the mass into its equivalent form of energy, right? It's the mass, so however many number of grams or kilograms times the speed of light squared. The speed of light is 300 million, right? So automatically, have 300 million times any amount of mass. So you've got a ton of energy. So the idea that mass and energy can convert between each other is strange, but very, very true, very obviously true. So this is just for reference, for numbers for you, for calculations. The periodic table always lists the average atomic mass, and that's the average of all of the different isotopes, all of the different versions of the atom, with each of the possible number of neutrons that are observed. There are also tables that can give actual masses of each isotope, and they're called nuclide charts, and it's a lot of information. But in these nuclide charts, it'll actually show, in lithium-6, so the lithium-6 isotope, where it has a mass of 6, the actual atomic mass is 6.015, and the natural abundance is 7.6% or so of the lithium found in the world. Is that. And then the lithium-7 is way more common, 92% of the time, or almost 93% of the time, and it has a mass of 7.016. Right? So there's numbers that, there's more information than just what's in the periodic table for chemistry. This is basically the periodic table extended for physicists. And so the masses of the proton, neutrons, electrons, right, are all added up for a given isotope. And physicists actually pay attention to the electrons. Chemists are able to get away with it because the precision needed for chemistry is much, much, much less, right? So chemists pretend that the mass of the atom is just the neutrons and the protons. Physicists, you'll see, don't do that, okay? But if you add up the mass of the protons, neutrons, electrons, and so on, the result is always slightly larger than the actual atomic mass. Okay, so if you add it all up, and it should be, 10 atomic units, it ends up being less than the actual, when you measure it, it's less than that. So there's always a little bit of mass missing. They call that a mass defect. Okay, and that mass defect exists in that system as energy. Okay? The equivalent version of the mass as energy instead. That energy is literally the energy that's holding the nucleus together. It's the binding energy, they call it. It's the energy holding the nucleus together. Okay, we'll see more about binding energy soon in the context of in the next lesson about releasing energy. how that works. Okay, but that's just think of binding energies, energies holding the nucleus together for now. When we're talking about energy units, the joule is way too big of a number, and so each much smaller unit of energy is needed. And so they use what's called the mega electron volt, or MEVs. So if you hear someone talking about energy in nuclear physics, they'll always talk about, oh, it's a certain number of MEVs. Okay, one MEV is only 1.6 or so times 10 to the negative 13 joules. It's a very small unit of energy. But that's because the amount of energy we're talking about for each individual nuclear transmutation, radioactive decay, and so on, the energy given off is extremely small. But there's an even bigger, extremely the large number of those reactions happening. So the amount of energy given off can be quite a lot, even though each individual one isn't releasing a whole lot itself. So here is a sample problem. Okay, we're going to calculate the mass defect. We're going to compare look at the mass of the actual atom versus what the mass should be. Okay, so we're looking at lithium 7, and so the actual mass is 7.016, 00. They've measured it to that level of accuracy and precision, so the mass is that. The mass defect, though, you look at what the mass should be, and basic chemistry knowledge, we have 3 protons, we have a total mass of 7, so we think it is like, you can calculate it should be 4 neutrons, right? So we should have 3 protons, we should have the 4 neutrons, we should have the 3 electrons that match the 3 protons, and so we should have 3 of that and 3 of that, and 4, 4 of that and 3 of that. I get my numbers mixed up here, but yeah, 3 of the proton, 4 of the neutron, and 3 of the electron. Okay, so again, back here we had the atomic mass units of each of these things. Protons and neutrons aren't actually quite the same mass. That's just chemists pretending, or it's close enough for chemistry, right? So if you have a chemistry background, you might be surprised to hear like, oh, they're not actually the same mass. They're just really close, right? Close enough for chemistry. And so the mass is 7.05813 and so on. And so you can see that the actual mass of 7.016 is less than what it should be, right? So this is what the mass should be, but the mass is only that, which is less. The missing mass is, again, the energy that's holding the nucleus together. It is kind of weird to think of, but it is just the way the world works. It's just, the things you discover when you look at things closely enough, right? So the mass defect, just the subtraction of those two numbers, right? The mass defect, that's the amount of missing mass, okay? So the mass defect is that amount. If you multiply the mass defect by the conversion between, atomic units and kilograms, so 1 atomic unit is this many kilograms, and so you have this number. Just think of it as a ratio. I would have a hard time remembering what I need to do to convert between all these random, weird, unfamiliar units. But you just need to look up the conversion factor, right? How many kilograms is an atomic unit? And Google will spit that out. I can't do it right now because the network's still down because of the cyber attack. But that'll be a weird thing to hear later on. This video gets used again, and we forget about that having happened. But, oh well. Anyways, the number of atomic units is the 0.042, and so obviously you have to multiply by 1.66 times 10 to the negative 27 to get the number of kilograms. Okay, so that means that's the number of kilograms that are missing. Okay, so they're saying there's 2 extra digits carried. You can only really trust the 6.99, I guess. They're addressing significant digits there. Again, you'd carry lots of extra digits during calculations, and we're not done with this yet, so that's why they're doing that. And so we want to figure out how much energy that is, right? So we can get the energy equivalent of that by doing the number of kilograms times the speed of light squared. So that means that there's this is how much energy is tied up as holding the nucleus together. So that's the binding energy. And you can convert that to mega electron volts so that it's an easier to picture number. The answer ends up being 39 mega electron volts. That's a lot easier to say and write down and work your numbers with than 6.295 times 10 to the negative 12. So 0.12 zeros You know, 11 zeros, I guess it would be. So the conversion between joules and mega electron volts, as long as you know, 1 mega electron volt equals a certain number of joules, you just look up that fact, and then you can do a conversion to set up the ratio, joules to mega electron volts, right? The joules to mega electron volts known ratio, the number of joules you have, and you can tell here to go from this number down to a 1, you'd be doing the 1 divided by, so second divided by first, right? 1 divided by the 1.602. So basically divide by 1.602, which is what it shows here. I've added this ratio way of doing this to help you understand how the textbook magically knows to divide by 1.602 times 10 to the negative 13. Okay, so I would definitely sort of make note of these conversions that you're going to need to do. These known ratios are important. That's the stars and so on, right? So a known ratio here for atomic units to kilograms, and a known ratio. It's just like knowing that there's 100 centimeters in a meter and 12 inches in a foot. It's all you just need to know some of these conversions to be able to use them. If you know the conversion, it's not complicated, basically. So that we managed to get, the 39 mega electron volts. And since we want mega electron volts as a easy to refer to number, so how many mega electron volts is the binding energy of lithium 7? What's the binding energy of iron? What's the binding energy of all these different elements, right? We want to be able to do that sort of more easily. So instead of starting with the atomic mass defect, converting to kilograms, and then converting to joules, and then converting to mega electron volts, we're going to just be able to convert them directly. Okay, I'll show you how that works. So basically, we know that that this gives us the amount of energy, right? But the conversion, if you look at how does this work? I'm trying to think of how to say this. So basically that ends up being 930 mega electron volts. So we have basically a known ratio. We have this ratio of atomic mass units to mega electron volts is a 1 to a 930, right? So we can just do the 0.42 number times 930 directly and get the number. So basically just multiply this thing by 930 instead of having to think of the 3.0 times 10 to the 8 squared and all that stuff, right? The other way they show this, they show it as in the end here that this 1 atomic mass unit times c squared equals this 930. So this is an atomic mass unit, right? That's how I was able to do the conversion before. We had to just have 1 atomic mass unit is equivalent to 930. So they say, okay, well, or you could look at it as c squared equals 930, and so you can just get the answer that way. You can just say, whatever your atomic mass unit is times 930. And so that's kind of the easiest way in the end, really, but I wanted to show 2 ways as to why it's true. So whatever your atomic mass defect is, literally you can just multiply by 930, and it'll give you the number of mega electron volts, which gives it, again, the same result as going from atomic mass units, which is mass, right, to kilograms, which is mass, to joules, energy, to mega electron volts, energy. So we need these small scale mass and energy numbers in order to deal and work with these very small numbers. Okay, so that's just more practice for you to do the same thing. So the nuclear fuel, uranium-235, for example, what happens is if a neutron from another, they have maybe something that triggers this to happen, or you just put a bunch of them nearby, and if one of them happens to give off a neutron, then this one absorbs a neutron and gives off, notice it gives off two extra neutrons, right? And then those 2 extra neutrons hit another uranium and give off another 2 neutrons, and then it's called a snowball or a snowball factor chain reaction, right? So you get this this one gave off 2, so then that gave off 2, and it multiplies from there, right? So the equation from this, we have this energy given off here by that, and so this chain reaction here would give 7 million times as much energy as the same mass of dynamite exploding, right? It's a very powerful thing. Yeah. So So this is that neutron moderation. This is the information about the CANDU reactor, about you have to have, if you have heavy water nearby, it moderates the neutrons and makes it so they can actually react with the uranium atoms when they get to them. And so it causes more reactions, and so you get this chain reaction effect. And so if that moderator isn't there, that doesn't happen, and the whole reaction stops, right? This is just another, this is just another chance to see the idea of the mass defect and the amount of energy released stuff, right? So if you look at the mass of each of these things, we have the atomic mass numbers for all of these numbers. If you looked at the amount that's missing, right, we'd analyze and see how much mass is missing, and we'd multiply out and see how much energy there was released. So all right, so yeah, so you just have to look at the amount of mass you started with and the amount of mass you end with, and you have this like missing mass, right? And so then that missing mass can be converted to kilograms and then converted to joules and converted to mega electron volts, or you could just multiply it by 930 and get the number of mega electron volts, right? So, you know, all those numbers of all those individual conversions lead to this same number finally of 181, but I don't know, why wouldn't you just do this, right? But some people like to sort of do it from scratch, because then you have, you know, sort of you can carry it all through and say, okay, I understand why all this worked. But really, in the end, like after you've done it a bunch of times, like I can just multiply by 930. I'll just go ahead, right? Just know that's the conversion from atomic mass units to mega electron volts, just like knowing any other conversion. Just like knowing 12 inches in a foot. So it's not any less valuable. It's just direct. So the nuclear fusion releases that. Now notice that in that one individual reaction, that's not a lot of energy, right? Because that's a very small amount of joules. But you have to realize that billions of these reactions happen very, very quickly, right? Because the number of atoms in something is just in a sample like the size of the pencil eraser, you know, there's an unimaginable number of billions of atoms. So same kind of calculations there. Fission, I don't know, whatever. I was just a Google picture. There's your CANDU reactor. We already talked about that enough. And I don't know, that's just like a sample there. That fuel bundle has a whole bunch of like, you know, eraser-sized pellets that just can power the generator for quite a long time, so on. I already talked about a lot of this stuff. It's just sort of official pages to do with it. So there's a type of reactor called a breeder reactor. I honestly don't know a ton about this, but basically they're possible to use, and they can actually produce the products of a breeder reactor can then be used again and again. And so basically you can get more energy out of nuclear material. So there's some issues here. Notice that one of the portions, or one of the parts of the process here, uses liquid sodium. I don't know if you've had a chance to see the sodium and how it reacts with any moisture in the air or water or whatever. It's extremely dangerous and explosive. So basically these breeder reactors are quite dangerous. They're a little harder to control. And so, you know, there's a problem there in terms of just the reliability and safety of them, right? So, but also they're a lot more dangerous just globally, because they produce basically, as part of their process, they produce plutonium and they produce radioactive material that is a key ingredient of nuclear weapons. And so if it was really common to use breeder reactors around the world, yeah, we'd be able to produce more energy and have less nuclear waste, but we'd also have a lot more extremely dangerous forms of nuclear material out there available for people to get their hands on and do bad things. So at this point, breeder reactors are not the type that we're using, right? And it's just something to know about. And there's the crazy charts to do with all the actual numbers and so on that physicists, use and so on. Really good videos here to check out. So if you watch the movie Oppenheimer, oh my gosh, I found it so boring, but the real story of Oppenheimer is kind of neat. And These ones here are a little bit more of like the ugly information, the truth. Like this video here is about how Kodak exposed or basically knew about the nuclear testing that's going on before it was released to the public. It was just a very hush hush, highly classified thing, but very worth a watch there. It's a little alarming, the kind of exposure to radiation that the U.S. government, was okay with. One of the things, the testing sites on the western coast of the U.S. and then the prevailing west winds, blew all that radiation across America, across the United States, and some even probably got to Canada. So there's like strontium 98 or something like that that's still in everybody's bones from the original mass numbers of nuclear tests they're doing. Kind of, yeah, the ugly part of nuclear fission in terms of nuclear bombs itself. So when talking about nuclear fission, you sort of have to talk about the good and the bad, I guess. So there you go. So that is nuclear fission for you. And yeah, so like and subscribe and comment and hit the notification bell, all those things, please, because that'll help push this content to more people that might need help with physics. Okay. So thank you very much for doing that if you don't mind, and I will talk to you next time. And of course, ask questions if you need help. Mind you, once the system's back up online, if you're going ahead with these.